I'd like to do a few problems from our textbook that involve using the normal distribution and the central limit theorem. These problems come off of page 291 and page 292 of our text in section 6.4. So I'm going to do numbers 9, 13, and 12, and I've chosen to do them out of order for a reason that, well, doesn't matter that much, but we'll talk about along the way. In number 9, safe loading of elevators. The elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds, 27 passengers. Because 4,000 pounds divided by 27 is 148, this converts to a mean passenger weight of 148 pounds when the elevator is considered full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Based on data set 1, body data in Appendix B of our textbook, assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. So they're telling me to assume that adult men's weights are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Find the probability that one randomly selected adult male has a weight greater than 148 pounds. Well, let's see, 148 definitely below the mean of 189. We're asked to find a probability of a more than, so we're shading to the right there in our normal distribution. So here in part A, we'll be using normal CDF in our calculator. The leftmost place that I've shaded is 148, and now I need to act like I've shaded forever, so I'm going to pick something so large that it might as well be infinite, so far away from the mean that it's actually ridiculous, and I always like to use 10 to the 99th for that. And then I'll need to enter in the mean of 189 and the standard deviation of 39. So let's see what happens. So I go into the distribution menu by hitting second vars. I go down to normal CDF. 148, comma 10 to the 99, comma 189, comma 39. I press enter and I get a probability of 0.8534 to 4 decimal places. So there's an 85.3% chance that one randomly selected adult man has a weight of 148 or more, so probability 0.8534. That's a pretty common occurrence. Part B, find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148. All right, so now I'm talking about taking a sample of 27 men and looking at their mean weight. The central limit theorem applies because my original population was normally distributed. So this isn't the distribution of adult men's weights, this is the distribution of sample means. The mean, mu sub x bar, is equal to the original mean, but the standard deviation gets smaller by dividing by the square root of the sample size, which here is 27. So I actually don't need to know exactly what that comes to, but I'm going to look at it just to see. That comes to about 7. A much smaller standard deviation. All right, so 148. Still more than. Selected 27 men, mean weight greater than 148. So we're still using a normal CDF. It looks just like this one, starting at 148, shading to the right so far that we might as well have shaded forever. The mean, but now our new standard deviation. And I could type in 7.51, but I'm just going to make the calculator do the heavy work. And that way I don't have to worry about any rounding. Sorry, I was writing off the bottom of the screen there, but I have normal CDF, 148, shade all the way over, so I have a 10 to the 99th, the mean and the standard deviation. All right, so normal CDF in the calculator. Type in what I have written down there. and we get a probability that's really close to 1, 0.99, and a whole bunch of 9s. Let's see, 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 7, 6, 5. In fact, we could just say that was just rounding to almost 1. It is a very high probability. It is almost certain. Now the important part of this problem, C. What do you conclude about the safety of this elevator? Well, part A doesn't matter. That's probably getting one person who weighs over a certain thing. You have one person on an elevator, they're certainly not going to, by themselves, violate this 4,000-pound capacity. Putting 27 people on it, that's what we're worried about. We're worried about having a full elevator. And there's almost a certain chance that with 27 people on that elevator, they're over the weight limit. Their average weight's 148, which means 48 times 27, well, that's 4,000 pounds. They're over the weight limit. It's almost certain that we'll be over the weight limit. So that's what we need to write down. Because of that answer in part B, it is almost certain that we will overload the elevator with 27 people on it. I would recommend to whoever is managing this elevator that they significantly lower this number as to not have this high of a probability of overloading the elevator. So that's number 9. I want to move on now to number 13, which is over on page 292. Redesign of ejection seats. When women were finally allowed to become pilots of fighter jets, engineers needed to redesign the ejection seats because they had been originally designed for men only. The ACES II ejection seats were designed for men weighing between 140 pounds and 211 pounds. Weights of women are now normally distributed with a mean of 171 pounds and a standard deviation of 46 pounds. So now I have a distribution of women's weights, a mean of 171 pounds and a standard deviation of 46 pounds. Part A. If one woman is randomly selected, find the probability that her weight is between 140 and 211 pounds. Those were those original safety requirements for these seats that had to be redesigned. So between 140 and 211. I don't think this is too well to scale here what I'm shading, but it'll let me understand what to use in my calculator. I'm using normal CDF. And I need to find the probability between 140 and 211. I'll tell the calculator the mean and the standard deviation. All right, and this probability comes to 0.5575. So 56% of women would fall in that range, which honestly, if you're trying to design a seat for a fighter jet, you probably want more people to be able to safely use it, or at least that's what I would say. Part B, if 25 different women are randomly selected, find the probability that their mean weight is between 140 and 211. So now we're in that situation again, where instead of the distribution of weights, we're looking at the distribution of sample means. The central limit theorem applies because my original population was normally distributed. The mean of all the sample means, mu sub x bar, is the original mean. But the standard deviation has shrunk. It's 46 divided by the square root of the sample size, which is here 25. So I'll just be dividing by 5. And just like last time, I'm going to write down what that is just so I know. I have my calculator off screen here, and I get 9.2 pounds. So The distribution of sample means has much less variation. That's one of the things the central limit theorem gives us. And now we're asked for the probability of their mean weight of these 25 women being between 140 and 211 pounds. All right, so I need to use normal CDF in my calculator again. All right, so 140 to 211. The mean and a standard deviation. So 46 divided by the square root of 25, and I could just type in a 46 divided by 5, but your calculator is capable of doing all of the heavy lifting there. So let's see. Go down to normal CDF. 140 to 211. The mean is 171. Now the standard deviation, 46 divided by the square root of 25. And I get 0.9996. All right, so a very large probability there. Not quite as high as the one on the part B of the last problem, but still very high. And again, we're asked a part C. When redesigning the fighter jet ejection seats to better accommodate women, which probability is more relevant, the result from part A or the result from part B? Well, in the elevator scenario, we picked part B because 27 people could ride in that elevator at the same time, and that was the more dangerous situation. One person riding in the elevator doesn't really affect the weight limit. The ejection seats have a much different principle. One person flies in an ejection seat at a time, so only part A applies here. This is the probability we care about. A sample of 25 people never fly in the ejection seat at the same time, so part B, while good practice for us, does not actually apply to redesigning those fighter jet seats. So there are problems 9 and 13. I wanted to do those in a row so that we could compare why part B is important in number 9 and why part A is more important in number 13. In just a moment, I'm going to record a solution to number 12, and that video will be posted right below this one.